wherever you are. Welcome to our webinar on JMAG and SIMBA. Thank you for joining us today. My name is Srihari Gangaraj. I will be your lead presenter. I am joined by my colleagues, Guillaume Fonte and Riako Imamura, who will be sharing insights during this session. The title of today's webinar is 1 plus 1 is equal to 3. How combining power electronics and motor simulation boosts electric vehicle powertrain design. Now, this isn't just a catchy phrase. It reflects the idea that motor and inverter systems cannot be optimized in isolation. The real performance gains comes when they are simulated together. Before we dive into the presentation, I would like to take a moment to highlight why this topic matters and give you some background about this. Next slide, please. So this is our agenda for today. We will start off with a quick overview and show you what we will cover in this session. Then we will discuss the core issue in electric vehicle drive simulation, how to evaluate loss with both motor and inverter. We will explore two methods of solution of modeling the motor and inverter system. And finally, we will touch on other electromagnetic models that support different power electronic simulation workflows. In the end, we will also have time for question and answer. I see that we have about 60 participants. I hope you can all hear me and you're all able to see the slides. So now let's dive into this topic. I have been in the electric vehicle and electric drive simulation for almost 25 years, specifically in the last 15 to 16 years. I've been working in General Motors and Stellantis on the simulation and optimization of electric powertrains. Now I am with PowerSys, and I felt that simulating the motor alone has a few drawbacks, and simulating the inverter alone has some drawbacks. So it is very essential to optimize the motor and the inverter together, because we know that the value of the electric vehicle heavily depends on how good the electric drive is. It is the heart of the performance, efficiency, and user experience. That's why engineers, we're always working to make the drive system more efficient, smaller, cooler, and faster. The electric drive, just so I set the context correct, the electric drive means the motor and the inverter together. Their interaction shapes the overall drive performance. When we design both together, something interesting happens. So 1 plus 1 doesn't equal 2 anymore. It equals 3. And by the end of this webinar, you will see what we mean. Better inverter and control can reduce the cost and the weight, as you see from this picture here. The inverter coupling affects the efficiency, and we will show you a couple of examples on that. Thermal management also depends on the power electronics, specifically the junction temperature and the losses in the inverter influence the motor thermal loads. Control dynamics cannot be captured without the inverter, as you see from this picture. Motor harmonics, they also need joint analysis between the motor and the inverter. Drive cycle optimization, it requires a system level view. A real world performance optimization like WLTP or FTP requires simulating how the motor and the inverter respond dynamically together. So all these reasons that you see together, when you put together, you'll see a small cartoon like the face of a lion or a Simba, and that's where the word Simba is coming from. Before we move further, I would like to take a moment to introduce about ourselves, who we are, the company that we work in, PowerSys, and also highlight our background. And now some of you may be familiar with us, but I still want to remind you about the role we play in electrification and the simulation ecosystem. Next slide, please. This is about us. Now, next slide. So we are on a mission to have zero prototypes. We are focused on simulation and optimization of electric drive systems. We have been working with automotive OEMs and suppliers to cut development time and improve design accuracy. Our core strength lies in electromagnetic simulation, thermal modeling, electromagnetic optimization. Now we are bringing the electrical simulation together with the motor simulation, and that's what we're going to be showing today. Next slide, please. We have been around since 2002 and operate in 90 countries with over 50 simulation experts. Next slide. And we have clients in Detroit area, in Europe, including General Motors, and also many startup companies, technology companies, also companies in robotics and so on, who are all doing electromagnetic simulation either for the motors or for other electromagnetic components. Now, let's dive into the real core of this webinar. Now that I've talked about why this simulation is important and who we are, I want to introduce you to my coworker, Dr. Guillaume Fonte, who is our power electronics expert, and he will discuss about optimizing the electric drive and how it is done with JMAG and SIMBA. Guillaume, please get started. Thank you.
Yes, thank you, Sherry, for this introduction. As Sherry introduced, it's a big issue. Still waiting for remote control. It's a little bit lagging. Okay, so yeah, actually to introduce it, a big issue is the loss of relation both in motor and in its inverter. So on one side, we have here the inverter loss with the conduction and the switching loss of the power switches of the inverter. And on the other side, we have the motor loss. So for example, in the case of a permanent magnet synchronous motor, we have the DC couple loss, which are mainly due to the rating resistance, but also the torque, that is say the operation point. And we also have ion loss, AC couple loss, and magnetic loss, which depend on the geometry of the motor, the materials, and also the current harmonics. That's to say the inverter configuration. So the big issue here is to evaluate all the losses. And for example, what's happening with different operating points. For example, one at low torque, high speeds, and one at high torque, low speed. And yeah, also, how can we predict, for example, the influence of such parameters as the modulation strategy or the switching frequency? Indeed, that a higher switching frequency will lead to higher switching loss of the inverter. But it's much more difficult to predict the influence on the current harmonics, which will supply the motor. That's to say, on the iron, AC couple loss, and magnetic losses. So here, in this webinar, we are going to see how a combined workflow using SIMBA and JMAG can help engineer evaluate both losses in the motor and in the inverter in order to make better design decisions. So now I'm giving the floor to Ryoko, who will detail the modeling differences of motor and an inverter that we can handle.
Thank you, Guillaume. Okay, then let's move to the next slide. Okay, in this slide, we will compare two common methods for modeling electric motors in a motor inverter simulation. And on the left, we see the lookup table method, which uses pre-computed data like inductance or flux linkage mapped over current and rotor position. The biggest advantage here is the fast runtime, which makes it great for system-level simulation or real-time application. However, lookup table needs to be degenerated for every new motor configuration, which limits flexibility. They also cannot capture demagnetization effects, magnet losses, or fault behavior with unbalanced current. So here's another method, that is a finite element analysis, where magnetic fields, losses, and faults are calculated in details using geometry and material properties. This method is highly accurate and supports any change in motor geometry or materials, FEA can capture magnetic loss, demagnetization, and drive force, making it suitable for robust design and failure studies. The downside is a slow runtime, especially during the time-stepping simulation or multi-parameter sweeps. Okay, now we review the motor side, so I'll move to the inverter. So here at the top, we have the ideal switch models. This one does not include any conduction or switching loss, so it is only useful for the basic system level simulation. It runs fast and helps with early stage control strategy development. The second model is a thermal switch. This model adds conduction and switching losses based on device data. It is much better for loss evaluation and early thermal analysis. At the bottom, we have the detailed switch model. This represents the real-world device, including nonlinearity, capacitances, and parasitics. It captures switching ripple effects and gives the most accurate results. It is suitable for high-fidelity analysis, especially when simulating EMI, ripple losses, or detailed gate drive behavior. SIMBA supports all three models, which let you choose the right level of details. Okay, with both motor and inverter modeling strategy understood, let's see how SIMBA and JMAG work together in practice. So, this slide, we will see that how the SIMBA and the JMAG work together, and in the top left side, SIMBA covers ideal switches, thermal switches, and detailed inverter models with JMAG-RT models, which are pre-computed lookup tables from JMAG. And this setup runs fast with limited flexibility of JMAG-RT. On the right top, we see where JMAG designer performs full finite element simulations of the motor using ideal switches. It can be run standalone for high accuracy motor analysis using real geometries and magnetic materials. However, the switch is limited because it is ideal switch. Then here comes the last one. At the bottom, we combine the detailed switches in SIMBA with direct FEA simulation from JMAG. This is the highest fidelity option. Real-time coupling between inverter and motor models for accurate loss, ripple, and fault analysis. SIMBA and JMAG together give you the flexibility to pick the right trade-off for your project, speed versus accuracy. Okay. Next, going back to the Guillaume, and then he will introduce actual example scenario for SIMBA JMAG coupling analysis.
Yes, thanks, Yoko. Let's take back the control. Okay, thank you. So, trying to move to the next slide. Yes, that's perfect. So, so here for this first solution, we're going to consider the complete electric drive model in SIMBA using a JMAG-RT model. So for this example, we're going to consider a PMSM on two operating points and with two modulation strategies and different switching frequencies. So for the inverter side, SIMBA can easily handle it, and a thermal description of power switches used to compute the power switch losses of the inverter. This thermal description is provided as XML files, which can most often be downloaded on manufacturer website. So on the motor side, we use what we call a JMAG-RT model. So here, RT stands for real time. So these RT models are generated from JMAG finite element analysis and are exported as lookup tables. And these lookup tables provide the dependence of flux, inductance, torque, loss on the current amplitude, current phase, and the water position, which are going to be determined in SIMBA. So yes, SIMBA will use this RT model in order to quickly simulate the motor behavior with a good accuracy. And that's one point that we're going to see in this webinar. So this first solution with SIMBA JMAG-RT offers a very good compromise between simulation and speed accuracy. Okay, so for the first step of this first solution, here is the complete design built in SIMBA. So you can see that in blue, we've got the power stage with the inverter, its motor. In yellow or orange, it's the thermal stage connected to all the power switches. In green, this is the control stage. You can see here a DQ control to apply a Q axis reference of the currents, that is, say, the torque. And the speed is imposed in the mechanical stage, which is in red here. So for the first step, which deals with the thermal description of the power switch, here we use a silicon carbide MOSFET from Wolfspeed. And so this thermal description has been downloaded from Wolfspeed's website as an XML file, as I already said. And this data provide the connection losses for different currents, but also the switching energies or turn on, turn off for different DC bus voltage, temperature, and current. We also have the thermal impedance of the module. So with all this data and the simulation results of SIMBA, SIMBA is able to compute the losses of the power switch, but also the junction temperature. So now let's go back to the global design to discover the step 2. So the step 2 deals with the JMAG-RT model integration into this complete SIMBA model. So here you can see on the red the PMSM block. So here, this block wraps the JMAG-RT model, which is, as I already mentioned, these are lookup tables which provide the dependence of the flux, the inductor, torque loss on the current and the rotor position. So now let's have a look at how is built this JMAG-RT model. So the start point is the JMAG designer. So you can see here the screenshot of JMAG workspace, where the geometry and the materials are defined. And I would just say that the lookup tables are generated once the FEA simulation is run. And now I'm going to let Hilko explain, expert of JMAG, and she will explain all this process.
Okay, yes. Then let's move to the next slide. And so here we use that tool called JMAG-RT Library Manager that is in a package of the JMAG. So okay, here's a small video of this. First, we need to specify that which JMAG input file we want to use. So first, we set the file name here, and then once the input file is loaded, we see that this menu. And here we set the motor specification information as a node. And then next, we go to the create tab, where actual operating points in the lookup table will be defined. In here, we will define the operating points like for the inductance, torque, and the iron loss tables. And then first, we set the current, and then here we use the automatic function. And then now we are setting the speed for the iron loss table. So, and then JMAG-RT has a parallel computing capability. So here now we set the 4 to use the 4 cores. Okay. Then now we set that overall operating point 209 points. So click OK, and then go back to the first menu, and then create a model. And you will get the JMAG-RT model for the RTT file. Okay. Then I just want to go to the next slide. Okay. So once we get the RTT file, next is that where SIMBA comes into that stage, and then here we will specify that RTT file. So in this diagram, we see that motor block model in the center. We call that the JMAG-RT motor block. And then when you double click this block, we will see that JMAG-RT PMSM properties diagram. And then in this diagram, at the top, we define that name of the motor block and set the path to the RTT file, which we just created. Then let's say we run this SIMBA file, then this is what you will get. And then here let's say we did a comparison of the two PWM strategies, SVPWM and DPWM, with the JMAG-RT plus SIMBA model. And the top plot shows A-phase current waveform. And SVPWM gives a smoother, more sinusoidal current, while DPWM introduces more notches due to its clamping behavior. Now, look at the middle plot, iron losses over time. DPWM shows slightly higher iron losses than SVPWM. This is expected because DPWM will bring in more harmonics in the current, which increases iron losses. And, oh, sorry. Yeah, we are still on this page. And then at the bottom, we have switching losses. And here, DPWM performs better. Its averaging switching losses is lower than SVPWM. That's because DPWM clamps one phase during part of the cycle, reducing the number of the switching. So we get a trade-off here. With this setup in the SIMBA powered by JMAG-RT, we can analyze these trade-offs so accurately, loss by loss, waveform by waveform. Okay, let's summarize this trade-offs with the two control strategies, space vector PWM on the left and the discontinuous PWM on the right. Each chart breaks down losses into copper, iron, conduction, and switching components. We are comparing performance at two operating points, high torque and low speed, and low torque and high speed. Starting with the top left, at 2000 RPM and 250 Nm using SVPWM, copper loss dominates. As the switching frequency increases from 20 to 60 kHz, switching losses rise steeply. And now you can see the same trend on the top right and the DPWM. Switching loss increases, but slightly less than SVPWM. And in the lower row, with high speed and low torque, iron loss becomes the dominant contributor. Especially under SVPWM at 60 kHz, iron and the switching losses increase significantly. DPWM still offers slightly lower switching losses here, but iron loss increases. So from this, we understand that dominant source of loss depends on operating point. One limitation of this analysis is JMAG-RT does not include eddy currents in the magnets. To capture those effects, we need to run a full code simulation between SIMBA and JMAG. So now let's discuss the code simulation of the JMAG and SIMBA. Unlike JMAG-RT, which uses pre-computed lookup tables, this method runs full finite element analysis in real time during circuit simulation. The diagram shows the two main components. On the left, we have the power electronic tool, in this case, SIMBA. And in the right, the FEA model created in the JMAG designer representing the motor with full geometry, materials, and meshing. The red arrows indicate two-way interaction. SIMBA provides real-time current waveforms and voltage command. JMAG computes the magnetic response, including torque, back EMF, losses, and even effects like saturation or demagnetization. This is especially useful for design validation, high-frequency behavior studies, and optimizing machine performance under realistic drive cycles. And so here, how to get input file for the code simulation in JMAG. So first, add the external circuit link condition and select the ports to link with external circuit. So here we selected voltage ports and current ports to export to the SIMBA. And we also want to export the motion information, so select the torque and the displacement. And once we created this list to export to the SIMBA side, our work is almost done. And then just export the input file and select the export JCF, and then type the name, my first direct coupling. Then now you get two files. The first one, .jca file, that is the JMAG FEA input file, include mesh, material, everything needed for the FEA. And the second one, .xml file, that is the link information to connect SIMBA and JMAG. All the port information we defined is included here. Okay. Now, let's say we got this input file for the co-simulation. Then let's see how to set up the direct FEA co-simulation in SIMBA. In this diagram, at the center, we have this JMAG direct coupling block. And then the panel on the right shows the JMAG direct coupling properties. And here we specify that the file path to the JMAG input file and port information, which we just got from the JMAG. And also we set the JMAG server library as the third parameter. Once this configured, SIMBA invokes JMAG during each simulation time, exchanging the signals bidirectionally. Okay, so then let's run this model. Then once we run, for example, we get this type of the outputs on SIMBA. The top plots show that the three-phase currents. These currents are nearly sinusoidal, but include high-frequency ripple and harmonic distortion caused by PWM switching. Unlike ideal models, these waveforms reflect the magnetic saturation and nonlinearities captured by FEA. And the bottom plot shows the electromagnetic torque waveform from the FEA model. You can see the ripple that comes from the throttling effect, current ripple, and magnetic cross-coupling. This is only possible because SIMBA is receiving real-time torque updates from JMAG FEA solver. As a result, we get a highly accurate picture of machine performance and the inverter operation. This type of simulation is ideal for validating current ripple, NVH sensitivity, and control tuning under real-world conditions. On this slide highlights the post-processing capability of JMAG during the direct coupling simulation with SIMBA. What you see here is the magnetic flux density distribution across the motor geometry at a specific time point. And this zoom in shows a hotspot marked as marks, indicating the area with peak flux density, likely near the tooth tips or rotor edge. These visual plots help us validate electromagnetic performance beyond the usual current and torque waveform. For example, we can check for localized saturation, poor flux linkage, or design bottlenecks around the corner or air gaps. That means while SIMBA is handling the circuit and control simulation, JMAG simultaneously solves and logs field data. This combination of waveform data in SIMBA and field data in JMAG gives complete visibility into motor performance, both globally and locally. Now, let's discuss the loss breakdown again, but this time JMAG-SIMBA co-simulation. And each chart shows losses across 5 categories: copper, iron, conduction, switching, and now magnet losses, which are only available in full FEA. The top row corresponds to high torque and low speed. The bottom row shows the low torque and high speed. As switching frequency increases from 20 to 60 kHz, we see clear trends. Switching losses grow rapidly. Iron and magnet losses increase at higher speed, especially in the bottom plots. And notice the small black segments on each bar. That's magnet loss, and calculated from the eddy currents in the rotor magnets. This would not show up in the JMAG-RT simulation, and is only visible in direct coupling mode. In this particular example, we see that magnet loss is comparable to the conduction loss. And when we analyze losses across a full system, motor plus inverter, we can better target where to optimize. And this view is essential for EV powertrain engineers trying to reduce heat generation, improve range, or select cooling strategy. This motor inverter coupled simulation in SIMBA, powered by JMAG, will enable you to smoothly identify those components that need to be optimized. Okay, that was our example of the motor inverter drive systems. In the last, we'd like to mention that the other models that can be simulated using co-simulation with SIMBA. Because co-simulation doesn't limit the application to the motor. This co-simulation framework, of course, allows us to link non-motor EM devices, such as transformers or inductors. And in this slide, we see some examples of the transformers, like high-frequency reactors or sheet coil transformers. All of them can be simulated using co-simulation, meaning the detailed EM effect can be captured in the power electronics simulations. Okay, let us recap how we optimize the drive performance using simulation. JMAG is used for motor simulations. It gives accurate results across different conditions. SIMBA is used for inverter simulation. It captures switching behavior and control. When we combine both, we can simulate the full electric drive. This helps us explore different inverter switching strategies. We can study how heat builds up and spreads in the system. We reduce torque ripple by tuning both motor and inverter together. Efficiency maps become more accurate. They reflect real-world conditions better. And at the end, we can make smart trade-offs at the system levels. And this co-simulation replaces guesswork with precision. The result is a better, smaller, and more efficient electric drive. So JMAG and SIMBA together create a high-fidelity co-simulation platform for electric drives, enabling accurate evaluation of motor control strategy, thermal behavior, and system-level efficiency under real-world conditions. Okay, thank you very much for joining us. That is all from us today. And then now, we move to the Q&A sessions. Okay, I'm not sure how to check the questions here. So,
I see.
do you see the questions?
Yeah.
Go ahead, Gabe.
Yes. Sorry. Okay, Shani. Yes, we have one question. And the question is that the first video you have shown, Yoko, was a bit too fast for the attendees. So he's asking that if we can share a link for it.
Oh, yes, of course.
Yeah. Anyway, this webinar will be available for the participants who have followed this webinar. Okay, we've got a second question. Can battery also implementable with its effects such as torque, thermals, and so on? I mean that this question with decision that can battery are also implementable in JMAG?
Maybe I can answer that question somewhat. I can share from my experience. So I understand what Mr. Furkan Duran is asking. In the electric drive system simulation, our goal is mostly to predict the range, for example, range of the vehicle. So just estimating the losses may not be sufficient. We also want to know, is the battery big enough? What is the state of charge? How hot is the battery, and so on. And in my past example experience, in a similar one, when we did the motor and inverter together, we did add a battery module from a third-party company as something like a Simulink or a MATLAB thing, because many times, the SOC prediction for a cell and a battery pack is more complex, and you want to have expertise in that and take that as a module, add-on module. And since SIMBA and JMAG have some scripting capabilities, there are opportunities to create that linkage with some other script if you have. We can talk offline. Furkan Duran, please contact us. We'll send a message to you. And we want to see what is it that you're interested in. And maybe there are some opportunities to do some workflow for you. Sorry, next question. There are a few more questions. Guillaume, if you want to take those questions.
Oh, yeah. I think it's one question for Hyoko or you, Shari. Does the constellation handle special harmonics as well as while evaluating losses?
The answer is yes. But one thing, need to be careful is this co-simulation, of course, can handle the special harmonics while evaluating the joule loss on the conductors. Then, when it comes to the iron loss algorithm is basically the frequency analysis. So iron loss will be the post-process. Hope this answer to your questions.
And just to add to that, Ryoko, yes, and that's a very good reason to do this kind of a co-simulation. That is exactly one of the reasons why we should do this. And you will see some surprises where if you don't do it, do this kind of simulation, and you do this and you'll see, oh, I should have been doing this coupled motor and inverter simulation to correctly predict the losses. We have another question from an anonymous attendee. Do you have quantitative analysis on the improvement of the results? JMAG plus SIMBA versus analytical models.
Yes, we do have that comparison. Maybe if you can give you your contact, maybe we can send you that information.
Yes. So anonymous attendee, please send us a quick message. We can share that. It depends, of course, very much on the size of the electric drive, but we can share with you some case studies on that. There is another question from Akhil Kumar. Can the capacitor bank be also included in the main supply to the drive system?
Yeah, I can answer this question if you want. Yes, of course, in this example, so this bus voltage has been modeled by a needle capacitor, by a needle voltage source, but of course, we can include capacitor bank as well as the rectifier, such as a passive front end or an active front end, and also to model the losses in this power stage.
Thank you. Oh, more questions. We have a question from Muhammad Abdul Majid. Oh, hello, Muhammad. I see that you used it in McMaster University. You have used SIMBA when you were at McMaster University. And thank you for your remark that it's a very powerful tool. We are continuing to improve it. But your question is about what is the major difference between SIMBA and the other tools like MATLAB and PSIM. And also you're saying, well, where does it fit when there's already a link between MATLAB and JMAG for co-simulation. I think Ryoko had presented some of that, but Ryoko, if you can please reiterate why this workflow is more powerful, more useful.
Yeah, so the difference between the MATLAB Simulink and SIMBA, there are a handful of the difference, or a lot of the differences. But the most important thing is SIMBA is really focused on the speed. And SIMBA is much faster than the matter of Simulink. So when we do the co-simulation, we need to run the Powertrain side that are faster than the switching frequency. So usually like let's say 0.1 microsec time step, and then keep running for the real time, like 5 minutes or something like that. And then if you do that with this FEA coupling, it's going to take a lot of the time if you do it in the matter of Simulink. Then SIMBA side can definitely speed up this Powertrain simulation side, and that will where you see the difference a lot. And then also, I can add more. Nobody's SIMBA will have that. Yes, this various level of the semiconductor switches from ideal to thermal, and then the details. SIMBA covers everything, and then you can see the effect of the this semiconductors thermal capability over the motor drive systems.
Thank you. Oh, we have many more questions now. I hope we can. We have enough time for all the questions. If we are not able to answer the questions, we will definitely follow up by email, or you can also email us. There's a question from Pawan Dakal. He's asking how fast does a single motor operating point coupled simulation takes? What would it mean for a complete drive cycle analysis? Rieko, can you give some ballpark? I think he's just asking.
Yeah. So actually, to answer this question, we need to think of the this FEA model's size, number of the elements. It highly depends on that. And so it's a little bit difficult to answer. It's a little bit difficult to give you a generalized answer. It highly depends on your FEA models. And, to get some idea, here's the example for this webinar. So in this webinar, we use that like 8K elements model, and then this we run the number 20,000 steps in SIMBA. Then in this simulation, when running the 5 electrical cycle, it took like around 20 minutes. This is where we are now. And then so if we try to do the complete drive cycle systems, 25 it is probably half day. That is the level of the simulation time, I believe now. Then to conquer this limits in terms of the speed, here are our cost simulation roadmap. We are planning to implement two things. One is a subcycling feature. That is a run EM FEA per n steps of the power electronic simulation. So skip some of the steps and then run the FEA. Second is a JMAG-RT direct coupling switching feature. Some of the JMAG user folks might be familiar with this. After reaching to the steady state while using JMAG-RT, switch to the direct coupling. That way we can skip that transient analysis part and then see that the steady state with FEA. That's how we strategize to speed up this co-simulations features.
Yes. And actually on that related question, there is a question from Joseph Jessis. He's asking, did we do only 2D JMAG, or can we do it with 3D also? Can you comment on that, Rieko?
Yeah. Yes. So this particular example was a 2D co-simulation. And then, of course, this co-simulation we can do with 3D too.
Okay, thank you. There is a question asking Asked by Thibaut Signor. He's asking, can we do the simulation with multiple motor controls at the same time and other converters such as U-grid systems?
Yes.
Yep.
So you mean you have the multiple motors in a circuit diagram. Currently, the first version of this simulation, we can't do it, but it is in a plan of the enhancing the feature, and it can be a possible. It will be possible soon. Yeah.
Sure. There's a question again from anonymous attendee. They're asking if we can monitor the temperature of each switch. They're saying that we showed the silicon carbide switches. They're asking if we can monitor the temperature and also compare the efficiency of different switch material and structures.
Yeah, that's definitely that's possible. That's the idea, to check if the junction temperature is not too high, and yeah, thanks to the data which are stored in the XML files, it's possible to well, it's the junction temperature is computed with the loss of the power switches.
Okay, very nice. Thank you. And thank you for asking that question, anonymous gentleman. If you are more interested, please send us a quick message. We can show you an example of how to track the temperatures using this workflow. We have two questions from Sai Praneeth Reniguntla. First question, he's asking for SIMBA, what are the voltage inputs, DQ voltages, general voltages? He also asked, is it just like SimScape, MATLAB SimScape?
Yeah, I'll say about the, yeah, I would say I can answer to the similarity. Yes, of course it's similar, but I would say that's of course SIMBA is more powerful. No, to, to be serious, the thing is that SIMBA is, according to us, much more adapted to solve systems with switches with idle switching events. We have developed a solver dedicated to this. So we have compared simulation time between SimScape and SIMBA is much faster.
Okay. And I think his follow-up question was, what are the voltage inputs? Are they DQ voltages or the general voltages ABC phase?
Oh, this JMAG block in SIMBA, it will accept the general voltage ABC phase.
Okay. Thank you. Then there is another question from Akhil Kumar. Due to an operation, there will be a voltage drop from the capacitor bank, which will further reduce the voltage to the motor. So the performance will be reduced. Akhil, you have a good point. We want to definitely follow up with you. Let us set up a meeting so that we can better address your exact use case. We are just 5 minutes short of the hour. So, Akhil, I think with a proper model and so on, we can kind of answer what you're asking for. Then there's another question about what's the advantage of JMAG compared to other FEA tools? Very good question from the anonymous attendee, and we are going to have a sequence of webinars to answer your question about JMAG. And the power of JMAG. So stay tuned to your email because it's not a short answer. And we will show how JMAG for electric motors for all other electromagnetic systems is more powerful than other tools. There is another question from Mariam Salehi. They are asking, is it possible to convert a new model from a JMAG designer to JMAG-RT and then connect it to Zumba?
Maybe SIMBA.
SIMBA. Yes,
so,
SIMBA. I mean, yes.
Yeah. Oh, yes. It is possible to connect the new model in a JMAG designer to JMAG-RT.
Yes.
Yeah. And then once you get the JMAG-RT model, yeah, it can be connected to the SIMBA. Yes.
Yes. And which brings up a good point. Again, if you are interested in a live demo, please feel free to contact us where we can walk you through some of these things of how to do this conversion. And any JMAG user who is interested in making this this connection, this integration, please ping us. We are available to help you and walk you through this process. And we are running out of time. I will take two more questions. One question from Ruchao Pupa Dubsin. Can we simulate thermal analysis in power electronic components to find the degradation of IGBT and diode or capacitors by thermal aging? We can, of course, like we answered before, yes, we can predict the temperatures of the switches, and we can give you the results of how the temperature is changing with time for different power profiles. But degradation of this switches, I don't know, one of you can answer. Do we have a degradation model or something?
Yeah, maybe I can answer that. This is Emmanuel from the SIMBA team. So actually what you can do in this type of simulation is you can extract the profile of the junction temperature of the semiconductors. Because we can model the actual thermal impedance between the junction, the case, and whatever coolant or cooling system you have. And from the profile of the junction temperature, there are analytical models that exist that can be used to predict the aging or the mean time between failure of the semiconductors. Those profile or those analytical equations are not part of SIMBA, but can be used as a post-processing. If you're interested, you can contact us and we can discuss this together.
Thank you. We are almost all. There's one other question about: do you have any experimental validation for your models? From Puya Taheri.
Yes. So for JMAG-RT, we do have that experimental validation. So yeah, if you contact us, then we definitely can send you that information.
Great. All right.
There is another question that I can answer. What's the
Yes,
background simulation engine used in SIMBA? Is it SPICE based or Plex based or something else? It's actually something different, something new that we have developed. And it's a solver that is that can do both piecewise linear analysis like Plex, but can also do nonlinear Newton-based simulation like SPICE. So the solver of SIMBA is a little bit like one piecewise linear solver and one SPICE solver had a baby together.
thank you, Emmanuel. Yes, very nice. I hope all of you learned something today about why we can do or why we have to do coupled motor and inverter simulation, and why it is within our reach to do this for your electric drive optimization. If any of you have more questions, please send us a quick note. We'll be happy to set up a meeting, and also this meeting was recorded, and we'll share the recording with you. I do see there are okay, no more questions. Any closing comments, Guillaume, Ryoko, or Emmanuel? Anything from you?
I just would like to thank everyone joining. Yes, thank you very much.
Can you please show that last page, Ryoko, simba.io?
Yes. Yes.
If you can. Yes. So, oh, I see one more question. Thibault Signor, GAN switch could also be used, right? Correct? They're asking.
Yes, that's right. Especially, for example, a GAN system provides thermal discussion XML files for their power switches, so you can use directly them in SIMBA.
Great, thank you. And please do visit our website. Those two website addresses are there. We have a PowerSys website, and we also have a SIMBA website that's dedicated for SIMBA. Both websites will show you a lot of information about our products and also the upcoming events. Please stay tuned for more JMAG and more SIMBA webinars in the near future. Thank you, everyone.